This conference will now be recorded. This conference will now be recorded.
So, very good evening, students. Today we'll start with a new chapter, and this is very interesting chapter. And the chapter name is Thermodynamics. It is a very important and very interesting chapter. We'll be able to learn many things here, which will be used as so in many science like chemistry, with thermodynamic law. We see there is law, engineering, in chemistry, in and many other branches of physics, etc. Previous chapter, remember, learned properties, thermal. Here discussed we had discussed much about heat transfer, a solid description of temperature. So in this chapter, we shall study the laws. In this chapter, in thermodynamics, we'll study the laws that governs thermal energy. Like we'll learn various laws which governs the thermal energy. Basically, here we'll study the processes of interconversion of work to heat, work into heat, and vice versa. So these things we'll learn from here. See, if we have to give an example of where work gets converted into heat, this is very simple example we can take out. Like in winter season, we generally rub our palms, okay? Rub our palms of our hands. Okay, so we see our palms will be a little bit warm when we rub against each other. Okay, one against other. So here, the work done in rubbing the palms gets converted into heat. Again, I can take another example where heat gets converted into work done. Can you give me some example? Work gets converted into heat that we have learned from this example, that if we rub our hands like one against the other, if we rub our palms one against the other, then heat generates. So there, work done in rubbing the palms will get converted into heat. But where heat gets converted into work, steam engine. In steam engine, this happens. So the heat of the steam actually helps to move a steam engine train. Okay, to run a steam engine train. Okay, so these are interconversion of work into heat or vice versa. Now we'll define what is thermodynamics. So what is thermodynamics? Thermodynamics is a branch of physics which deals with the concept of heat and temperature and interconversion of heat and other forms of energy. Not only heat, there may be other forms of energy, how they get converted into work. So we'll be discussing about the concept of heat and temperature and their interconversion in this thermodynamics branch. Okay, now thermodynamics and molecular physics, they have certain distinct like a certain difference in the treatment and etc. Thermodynamics some properties like we have thermodynamics is has actually thermodynamics is a macroscopic science. Macroscopic means the object which we can see in our naked eyes, the object which we can feel or we can directly measure are so those actually macroscopic involves in macroscopic science. Those macroscopic means macro or bigger objects, object parameter. Those involved in like science, those are called behind those macroscopic parameters, and science or science involved macroscopic objects. Okay, so topic science. So this statistics, sorry, this thermodynamics deals with the bulk system and does not deal with or go into the molecular constitution of matter. So molecular constitution of matter will not discuss in this because thermodynamics doesn't deal with microscopic situations or microscopic states. It deals with the macroscopic systems or noticeable objects. And thermodynamic description, see, it involves relatively few macroscopic variables of the system which are suggested by common sense or directly measured. So the parameters we will be dealing with in thermodynamics, which will actually suggested the variables we will be dealing with by some common in thermodynamics say or those can be measured directly like volume, pressure, temperature. Those are the macroscopic parameters which we will be dealing with in the branch of thermodynamics. Now, molecular description of gas is actually very complicated. Why? Because molecular description, in molecular description, you have to specify the coordinate of a large number of parts of gas. There may be huge number of molecules or atoms will be there. So if you specify the position coordinates and velocity of each of them, it is going to be a very cumbersome job. So molecular description, even in kinetic theory also, this details of coordinates and velocity is not involved. Okay, some average things are taken like distribution of velocities are actually considered the main fundamental thing in kinematics. Okay, velocity distribution generally they discuss much like much of things with velocity distribution, not the specification of the coordinates. Okay, so you can understand that the molecular description of gas will be far critical than the thermodynamic description of gas, because thermodynamic description involves macroscopic variables like pressure, then volume, and their components. So these are mass and composition. The pressure, temperature variables, volume variables involve thermodynamics. So these are macroscopic parameters: pressure, temperature, volume. Macroscopic in the sense we can feel it. We can feel it by our sense, and we can easily measure also. So that's why those are macroscopic parameters. Now we learn the difference between mechanics and thermodynamics. Like there will be, so the thermodynamics actually a very unique subject, and it doesn't have any correspondence with the mechanics. So how mechanics is different from thermodynamics, that we'll discuss now. In mechanics, the motion of system as a whole is discussed, right? So we discuss in mechanics what we discuss. I'll write and thermodynamics. So in mechanics, detailed motion, detailed motion of system as a whole detailed motion of system as a whole is needed to to discuss the mechanics of any object. Okay, it's details description of motion, like see motion under torque or force, all those things you have to specify the force and direction. You have to specify the position, and then how much position changes. Okay, position, velocity, then displacement, distance, etc. There are many parameters in mechanics, isn't it? And you need it like you need to deal with the motion of the system as a whole under the action of several forces or torques. But in thermodynamics, what is done is that motion of the system as a whole does not require. No motion is required here. No motion. Thermodynamics means no motion of the system as a whole is required. Then it is concerned with the internal macroscopic state of the system. So, but like thermodynamics deals with the internal macroscopic state of the body. Internal macroscopic internal macroscopic states of the body is important. Okay. All right. So if we take an example, you can understand when a bullet is fired, its mechanical state changes due to bullet is fired. The mechanical state changes due to increase in kinetic energy of its center of mass, but its temperature is not affected. But bullet pierce a wood and stop it, its kinetic energy gets changed into heat energy, and it heats up the bullet. Therefore, thermodynamics is related to internal disorder of motion of molecules, which involves with the change in the temperature. Okay, but it doesn't require to know how the bullet passes through a thermodynamic system. So in the thermodynamic system, basically, we don't deal with the details of force and motion of system as a whole, which we do in mechanics. But in thermodynamics, what we do, we define energy, okay, for a system, and we see the change in the system while the bullet is shot. Okay, so this is about thermodynamics and mechanics. Now we'll go to learn few thermodynamic parameters first. First of all, these are some definitions related to thermodynamics. What is thermodynamic system? We'll be frequently using these definitions in our discussions. So better to know what is thermodynamic system. Actually, a thermodynamic system is an assembly of very large number of particles having a certain value of pressure, volume, and temperature. So system generally what will be taking an assembly of a large number of particles, having certain having certain oh sorry having certain pressure denoted by P, volume denoted by V, and temperature T. Okay, so a system is an assembly, thermodynamic system is an assembly of a large number of particles having certain pressure, temperature, and volume. Okay, so when we discuss further, you will understand what is thermodynamic system. Okay, now we'll learn what is called surroundings. Actually, surroundings means, see, we have taken the system, and everything other than system is called surroundings. Everything outside system which have a direct effect of system is called surroundings. So everything outside the system, everything everything outside the system which can have direct effect, sorry, direct effect, excuse me, direct effect of direct effect on the system. So everything outside the system is called actually surroundings, which can have a direct effect on the system. Okay, this is called surroundings. Now, what is called thermodynamic variables? What are called thermodynamic variables? Thermodynamic variables. The quantities like pressure, volume, temperature, which we have been discussing, and sometimes mass, etc., will help us to understand or study the behavior of a thermodynamic system. Okay, so whenever we will be discussing a thermodynamic system, we'll see the pressure, volume, temperature, etc., how they are changing for a particular system. Okay, these are thermodynamic variables. Even we have some mass, etc., and another parameters like internal energy U, enthalpy H, then Helmholtz free energy A, etc., will come across in thermodynamics. But in your syllabus, I don't know whether you have uh, this free energy and all. If situation comes, we'll discuss. Okay, and equation of states. What is called equation of state? Actually, equation of state is the mathematical relation between pressure, volume, and temperature of a thermodynamic system. We'll write this. Okay, thermodynamic variables we have already written. So, what is equation of state? The mathematical relationship between the thermodynamic variables. Okay, the mathematical relation between various thermodynamic variables of a thermodynamic system is called equation of state. Okay, this I can give you an example. PV is equal to nRT. Okay, this is one of the famous equation of state. Now we'll slowly enter into the thermodynamics. Here we'll start with thermo thermal equilibrium. Actually, there are mechanical equilibrium in mechanical system. What is the definition of mechanical equilibrium? Mechanical equilibrium. So in mechanical equilibrium, what happens? Suppose if this object is at mechanical equilibrium, so this must be acted upon by equal and opposite force, F1, F2, and also acted upon by no net torque. Okay, that means actually no net, F net is 0, tau net is 0. Then mechanical equilibrium is established. Okay, this is about mechanical equilibrium where the net torque or net force will be 0. But how do you define thermal equilibrium or thermodynamics equilibrium? Actually, thermal or thermodynamic equilibrium is the one when there are various parameters like P, V, T, etc. Thermodynamic equilibrium means at any instant of time, if the variables are like P1, V1, and T1, if after long time also it remains as P1, V1, T1, then it is called the system is called that the system is at an equilibrium because the pressure, volume, and temperature, they are not changing. Okay, now we'll define thermal equilibrium. Actually, thermal equilibrium generally discussed with at least two objects or two systems. So suppose there are two systems which are said to be in thermal equilibrium with each other. Suppose I have an object A, object B. They are in thermal equilibrium. That means both of them have the same temperature. Okay, then only we can say both are in thermal equilibrium. Now, see, if we consider two gases A and B, they are confined in different vessels as you can see from here. So there are two gases A and B, they are confined in two vessels. Okay, and suppose the gas A has the parameters PA, VA, and TA, and the gas B has PB, BB, and TB. Sorry, I write all of them small. Okay, so suppose there are two systems A and B, like two gases A and B, they are contained in two different vessels. The pressure and volumes are respectively PAVA and PBVB. Now, if the two gases are separated by an adiabatic wall, so this is adiabatic wall, suppose adiabatic wall. So adiabatic wall actually a wall which does not allow heat transfer or energy flow of it, does not allow flow of it. So look what I am saying, that there are two gases A and B contained in two different vessels which have thermodynamic variables like that, and suppose these two systems are separated by Adiabatic wall, what is adiabatic wall? Adiabatic wall means it does not allow the flow of heat. Okay, so if they don't allow flow of heat, but we say they are in equilibrium, then some set of PA, VA and TA will be equal to PB, VB and TB. So this state may be at equilibrium, in equilibrium with this one. Okay, so any set of values of P, V and T will be in equilibrium, thermal equilibrium with the other one. And in this case, the separation between the two gases are adiabatic wall. What do you mean by adiabatic? Adiabatic system or adiabatic wall mean it does not allow the flow of heat. And for that case, any set of PA-VA will be in thermal equilibrium with PB-VB. Okay, now if the wall is changed. Now the wall is changed. See, the nature of the wall is now diathermic. Diathermal or diathermic. Let me clean and write. This wall is actually diathermic. Diathermic means it allows heat transfer or heat flow. Diathermic wall. So when the two systems which have PA, VA and TA separately, and they are separated by a diathermic wall, then there will be heat exchange between them. Such that the new states of A and B are in equilibrium with each other. Okay, so what we'll do, we'll discuss about this diathermal or the wall which allows the heat flow. Now you know what will happen. A and B, they will be communicating with each other, and the heat energy will flow in such a way that some other value of PA-VA will be in thermal equilibrium with PB-VB. And in this case, the temperature will be the same for both the cases, A and B, because it is diathermal wall. So diathermic wall allows the energy transfer. Okay. So in the second figure, what I'm trying to say, that A and B are separated by diathermic wall or conducting wall. The pressure and volume of the two gases changes to some other value. Suppose P PA prime, VA prime for A, and for B, PB prime and VB prime. And in these new variables, these two systems will be equilibrium with each other. And when they come to the equilibrium, there will be no flow of heat. Understand? This is called thermal equilibrium. So we had already discussed a little bit in the previous chapter also. There will be thermal equilibrium when there will be no heat flow or no heat exchange between one another. So here A and B, if they have temperature difference, then this PV and T that will change with each other. Like they will change to some other set of values. But when the thermal equilibrium is attained, there will be no exchange of heat energy. Okay? So this is thermal equilibrium. Now there is a subtle difference between thermal equilibrium and thermodynamic equilibrium. We'll little bit discuss about thermodynamic equilibrium. Actually, a system is said to be in the state of thermodynamic equilibrium if the macroscopic variables of thermodynamic state do not change with time. Okay, so this was thermal equilibrium. Now broadly we had discussed thermal equilibrium. Now we'll see what is called thermodynamic equilibrium. Thermodynamic equilibrium. So thermodynamic equilibrium means, see, suppose there are two systems or maybe a system. It has like system of gas system. Suppose it has pressure initially PA, VA. Now if it does not change to some PA prime and VA prime with time, if this changes into this with time, then it is not in equilibrium. No equilibrium, not in equilibrium. Equilibrium. But if the parameters PA, VA remains constant or does not change, do not change, do not change. If PA, VB, suppose, yes. If I can take any arbitrary PA, VA, PA, VB, anything arbitrary. So if let me write this as PA, VA itself. So if this does not change with time, then it is called thermodynamic equilibrium. Okay, now we'll go to the next topic, zeroth law of thermodynamics. It is very interesting topic, and this will provide you the concept of temperature. So what is zeroth law? I'll write the statement. It states that if two systems A and B are separately in thermal equilibrium, separately in thermal equilibrium, separately, sorry, with a third system C, then A and B are also in thermal equilibrium to each other. A and B, sorry, A and B A and B are also in thermal equilibrium with each other. Thermal equilibrium with each other. Okay. So what is the statement? It says that if two systems A and B are separately in thermal equilibrium, suppose there are three systems. This is 1A, this is B, and this is C. So if this A and B, they are separately, that means A is in equilibrium with C, then again B is in equilibrium with C, then from there it can be inferred that A is in equilibrium with B. Okay, if A is separately in equilibrium with C, thermal equilibrium, if B is separately in equilibrium with C, then A and B must be equilibrium with each other. So that is what is the statement. Okay, all right. So we'll see how it leads to the concept of temperature. Zeroth law of thermodynamics implies that the temperature is a physical quantity which has the same value for all the systems which are in thermal equilibrium with each other. Okay, so the temperature of a system determines whether it is in thermal equilibrium or not with another system. Obviously, if A and B are separately in thermal equilibrium with C, then temperature of system A and temperature of system C will be equal. That is Ta is equal to Tc. And again, if the B is in thermal equilibrium with C, then Tb is equal to Tc. Therefore, we can write Ta is equal to Tb. The system A and B are also in thermal equilibrium. I'll write over here so that you understand nicely. So zeroth law of thermodynamics actually implies that or leads to the concept of temperature. So look, actually we know the thermal equilibrium means temperature of the two systems must be equal. Then only we can say that two systems are in thermal equilibrium. Now when I say A is in thermal equilibrium with C, then it must imply that Ta is equal to Tc. For that, if I say the system B is in thermal equilibrium with C, then that also will apply, imply TB is equal to TC. Okay, that means the temperature of the object B exactly equal to the TC. Now look, see TC and TC are same. Then from there it implies that TA, T, since this TC is same for both this TA and TB, we can say that A and B in thermal equilibrium. So when A and B they are in thermal equilibrium, then TB is equal to TC, temperature for both of them same, and A is thermal equilibrium with C. So in that case, TA is equal to TC. So from here it implies that TA will be TB. Okay, so that's how this the modern concept of temperature as follows from the zeroth law of thermodynamics. So this law may be stated in the form of fundamental ways as follows. So there exists a scalar quantity called temperature, which is a property of all thermodynamic systems, which actually specify whether, or which is a necessary and sufficient condition for thermal equilibrium. So temperature is a physical quantity which actually determines, or which tells us about the two systems whether they are in thermal equilibrium or not. Okay, so today we'll stop it here. Next day we'll learn about internal energy, work, etc., and heat, etc. Okay, so bye for today.